Hello everyone, welcome to the video lecture series on circuit analysis. In the last session, we have seen the delta Y transformation and Y delta transformation, and as well we have tried to show or how to use multi-sim software. Now today we are going to use or see method of circuit analysis, which is chapter 3. So the purpose or the objective of this chapter is basically we need to consider what is the purpose of circuit analysis method, what are the circuit analysis methods. That means we are going to consider node analysis method, procedures or steps for node analysis method, and uh, apply node analysis method as well as node analysis with voltage source. So these are the contents we need to consider. So as introduction, in the last session, we have seen the way how we can determine the voltage across an element or current through an element, and the way how we use Y delta transformation or delta Y transformation to simplify circuits. So for more complicated circuits and networks, trace parallel analysis and Y delta transformation. That means we are using this part, the trace parallel circuit, Y delta transformation. Okay, so this technique are not enough to solve a very complex circuit. So we need to have, or we need to another approach to make circuit analysis for complex circuits. So this circuit analysis method will help us to solve the different complex circuits which will not be tackled by trace parallel or delta transformation. Okay. So the purpose of circuit analysis method is to determine the voltage across or current through. You need to consider here to determine the voltage across an element or cross current through an element of a circuit. So in this approach, basically, no modification on the given circuit while performing circuit analysis method. That means to mean that basically what we have seen in the last session, we are making a certain circuit modification to solve the voltage across an element or current through an element. Basically, when we are considering the circuit analysis method, the given circuit configuration will not be touched. Rather, we are going to develop a mathematical expression. Okay, so the two circuit analysis methods are the node analysis method and the mesh analysis method. Okay, so for node analysis method, voltage will be considered. Voltage uh, uh, will be considered. Okay, and for mesh analysis method, current variable will be considered. Current will be considered. So basically, today I'm going to discuss on node analysis. Okay, so the circuit analysis objective is to determine node voltage, and mesh currents. After that, we can determine the branch currents. And the circuit analysis tools we are going to use the Ohm's law and the Kirchhoff's law. That is the two very important or fundamental laws in circuit analysis. That means Ohm's law and Kirchhoff's law. Under the Kirchhoff's law, we are going to consider the Kirchhoff's voltage law and Kirchhoff's current law. So circuit analysis method for the node analysis method, we are going to apply the systematic application of Kirchhoff's current law. And for mesh or loop analysis, we are going to consider or apply systematic application of Kirchhoff's voltage law. That means the Kirchhoff's law will be considered in circuit analysis method. For node analysis, KCL will be considered, and for mesh or loop analysis, KVL will be considered. So before going to this circuit analysis method, basically we need to consider these terms. The first one is node. This point is term is basically very important for node analysis, which is a point where two or more circuit elements join together. Okay, two or more circuit elements connect together. We can consider essential node. Essential nodes, that is a point where three, that is more than three, or the minimum requirement for a node to be essential node, there should be three elements connected together. So an essential node is basically a point where three or more circuit elements connected together. When we consider branch, it's a path that connects two nodes. That means we can consider, for example, this is a circuit element. Okay, so you can see here. So this is a point, and this one is a point. So this point is this element will be connected. The two elements will be connected at this point, and at this point, this element and this element will be connected. So this is a branch. This is a branch that connects two nodes. A loop, a path whose last node is the same as the starting node. That means to make a loop, we need to return back to the starting point of the loop. A mesh, it's a very important point in circuit analysis. This is a term that is used to determine or for a certain independent loops in the circuit. That means a loop that does not enclose any other loop inside it. To mean that a loop uh, cannot be a mesh. That means we need to consider here a loop cannot be mesh. But the reverse is true. That means a mesh can be a loop. Okay, so a mesh is a loop, but a loop cannot be necessarily a mesh. So when we consider node analysis, we call it the node voltage method. We call it node voltage method, or node voltages are used as circuit variables, and choosing node voltage instead of element voltages. Instead of considering the voltage across an element, it is better to use node voltage, okay, as a circuit variable, which is very important to reduce the number of equations one must solve simultaneously. Okay, so we are going to use the application of Ohm's law to determine the branch currents, and we use the application of Kirchhoff's current law. So when we consider node analysis, KCL will be considered. When we consider mesh analysis, KVL will be considered. Ohm's law is common for both node analysis as well as mesh analysis. So we have a general steps to apply node analysis. So we have a given circuit with any number of nodes without a voltage source, but as a current source. So the node analysis of the circuit involves taking the following three steps. The first one is select a node as a reference. So this is the basic point we need to consider. That is when we are making a node analysis. That means a node as the reference. We need to select from the given circuit one node should be considered as the reference node. Then we are going to remain with n-1 nodes. That means we are going to assign voltages for the n-1 nodes. That means V1, V2, up to Vn-1, because one node is considered as the reference node. So that's we remain with n-1 nodes. So for this remaining n-1 nodes, we are going to assign the node voltage. So the voltages are referenced with respect to the reference node. So the reference node is very important to consider the other node voltage. After selecting the reference node and assigning node voltage for the non-reference nodes, so we are going to apply KCL to each of the n-1 non-reference nodes. So we are going to use Ohm's law to express the branch currents in terms of node voltages. And the third very important step is solve the resulting simultaneous equation to obtain the unknown voltage. So the number of non-reference node is equal to the number of independent equations to be solved. So we are going to determine n-1 mathematical simultaneous equation from the given circuit, because one node will be considered as a reference node. So for the reference node, there is no equation developed. So the first step in node analysis is selecting a node as a reference node or datum node. So the reference node is commonly called the ground, since it is assumed to be to have zero potential or zero voltage. So these are the symbols. The reference node is indicated by these three symbols. That means this one is one representation in electronic circuit. We can use this is another reference representation, and this one is also another reference notation, okay, or symbol. Let's consider this the given circuit, how we can apply node analysis. That means we are going to apply the steps, the three steps. The first one is selecting the reference node. then we are going to remain with n minus 1 nodes. So for the n minus 1 nodes, we are going to assign voltages. Then the second step will be the application of KCL, and Ohm's law. Then finally, the third step will be solving the resulting simultaneous equation. So as you can see, this is the circuit. This is the given circuit. Okay, that means apply KCL at each non-reference nodes as shown. You can see here, this is the reference node. As you can see here, this is a reference node. Okay, so we are remain with two non-reference nodes. Basically, totally, this circuit has 3 nodes. This is node 1, and this one is node 2. Okay, and this one is node 3. So from the 3 nodes, this node is the reference node. So we are remaining with the non-reference node, node 1 and node 2. So for the non-reference node, where V1 will be assigned for node 1 and V2 will be assigned for V2. Okay, and branch currents will be assigned, as you can see here. Branch currents will be assigned for these circuits. So as you can see here, at point one, I1 it is entering the node, capital I1 it is entering the node, and small I1 it is leaving the node, small I2 it is leaving the node, and capital I2 it is entering the node. Okay, so as we can apply KCL at this point. Okay, apply KCL at node 1. That means I1 and I2, they are entering the node, node 1. Okay, and I1 and I2, they are leaving the node, 1. Okay, so we can apply KCL. Capital I2 it is leaving the node, so we can apply I1, which is equals to small I1 plus small I2 plus capital I2. So you'll have I1 minus capital I2, which is small I1 plus small I2. Okay, and at node 2, we can consider capital I2 it is entering the node, and small I2 it is entering the node, and small I3 it's leaving the node. So I can write I2 capital I2 plus small I2, which is equals to small I3. Okay, so this is a mathematical expression at node 3. Okay, so we are going to apply Ohm's law to express the unknown currents I1, I2, and I3 in terms of the node voltage. And we need to consider here a very important consideration or point. We need to always remember that means current always flow from high potential to a low potential in a resistor. So we are going to consider this very important equations. Okay, so I1, you can consider here I1 it is flowing from node 1 to the ground. So V1 it is at higher potential considered to or with respect to the ground potential. So I can write I1 which is V1 minus 0 over R1, or in terms of conductance we can write I1 or small I1 which is G1 V1, and small I2 you can consider as flowing from in this direction. So V1 it is at higher potential with respect to V2 because the current is flowing from V1 to V2. So I can write small I2 will be V1 minus V2 over R2. Okay, so you can see here in terms of conductance, and you can consider a small I3 it is flowing from node 2 to the potential or the zero potential. So I3 will be V2 minus 0 over R3 So we are going to substitute these current expressions into the above equations. That means you can consider capital I1, which is I is equals to I2 plus V1 over R1. This is small I1. Okay, and this one is small I2. Okay, and this is equation 1, and the other one is I2 plus this is a small I2. This is small I2, and this one is small I3. Okay, so using this we can have the equation in terms of the conductance. So after determining the node voltage equations, okay, we are going to apply this mathematical solving or simultaneous equation solving method. That means substitution method or elimination method or Cramer's rule and matrix inversion form. That means solve the node voltage equation to determine the node voltage V1 and V2 using any standard methods. Either we can use substitution method or we can use elimination method. This is for uh, preliminary mathematics, which is solving simultaneous equation by substitution method or elimination method. And we can apply also matrix. We can apply also matrix by using Cramer's rules or matrix inversion. So to use either of the last two methods, one must put the simultaneous equations into matrix form, just as you can see here. So put the simultaneous equation in matrix form as we can have this, okay, which is this is the first equation and this one is the second equation. So this is the uh, a, a coefficient of V1 and this one is the coefficient of V2 for equation 1, and this one is the coefficient of V1 and this is the coefficient of V2 for equation 2. So we can have this matrix representation of the two node voltage equation. So you can use also, this is G1, this one is G1 and this one is G2, okay, conductance, and this one is minus G2, okay, and similarly here minus G2 and this one is also. So using conductance we can put the matrix equation using, this is using resistance and this one is using conductance representation. Okay, so based on this, let's consider calculate the node voltage in the circuit. Okay, that means you can see here we have a current source 10 ampere, it is entering this node, and 5 ampere it is entering this node, and the 5 ampere it is leaving this node. So we are going to apply the three very important steps. The first one is selecting one node as a reference. So this node is considered as a reference node. Okay, this is reference node. Okay, and the second step is assigning voltage or node voltage for the non-reference node. So as you can see here, V1 is assigned for node 1, and this is V2, which is assigned for node 2. Okay, and the other very important step is we are going to assign a branch currents. So as you can see here, I1, small I1, it is entering the node 1, small I2 it is leaving, and small I3 it is leaving, and small I5 it is leaving, and small I4 it is entering the node. Okay, so we are going to apply KCL for the non-reference nodes, Okay, so using this expression, we can write I1 it is entering node 1. Okay, I1 entering to node 1. Okay, and I2, I3, okay, they are leaving node 1. Okay, so I can write I1 which is equals to I2 plus I3. So this is equation 1. So I'm going to apply Ohm's law. Okay. That means here I1 it is 5 ampere, okay, and I2 which is equals to V1 minus V2 over 4, and I3 which is V1 over 2, So we can consider these are equation 2. These are equation 2. Okay, equation 2. Now I'm going to substitute these equations into equation 1. Substitute this equation into equation 1. That means I can write 5 is equals to V1 minus V2 over 4 uh, plus v1 over 2. Okay, v1 over 2. So you can see here, when you simplify, when we simplify 3v1 minus v2, which is equals to 20. Okay, so this is equation 3. This is equation 3. And apply KCL. Apply KCL at node 2. Node 2. Okay, at node. That means I5 and I1, they are leaving the node, leaving node 2, and I2 and I4, they are entering node. Okay, so I4, that is 10 ampere, and I1, that is 5 ampere. So I can write I1 plus I5 is equals to I2 plus I4. Okay, so I can write I5 minus I2, which is equals to 10 minus 5. So I5 is minus I2, which is equals to 5. So this is equation 4. So using this two equations, equation 3 and 4, let's apply Ohm's law. Apply Ohm's law. Okay? Apply Ohm's law. That means I5 is equals to V2 over 6 ohm, and I2, which is equals to V1 minus V2 over 4 Okay, so let's substitute this expression in equation 4. In equation 4, this is equation 5. Substitute equation 5 into equation 4. Yeah. That means V2 over 6 minus V1 minus V2 over 4, which is equals to 5. Then after simplifying, we'll have minus 3V1, okay, plus 5V2, which is equals to 6. So this is equation 6. Then let's solve equation 3 and 6 simultaneously. That means 3v1 minus v2, which is equals to 20, and minus 3v1 plus 5v2, which is equals to 60. So let's solve. So let's add together this. So you have, this will be cancelled. So 4v2, which is equals to 80 over 4. So V2 will be is equals to 20 volt. Okay, and we can apply 20 volt for V2. So you can consider 3V1 minus V2, which is equals to 20. Okay, so 3V1 minus 20, which is equals to 20. So 3V1, which is equals to 20 plus 20. So 3V1, which is equals to 40 over 3 V1, which is equals to 40 over 3 volt. So using this, we can determine V1 and V2. So V1 and V2 are the node voltages. V1 and V2 are the node voltages. Okay, so that's all about for this session. In the next session, I'll solve another problem. So please like and share my video lecture and subscribe the channel so that it will be accessible for others. Thank you very much.